So it is a pleasure to introduce Alexander Dalzell from Caltech, who is gonna talk about random quantum circuits and concentrate in log depth. So please, Alexander, the stage is yours.
Thanks, Daniel. Good morning to those of you out there like me in California. Good afternoon, good evening, I guess, to most of the rest of you. So yeah, this talk is going to be about random quantum circuits, and in particular about a property called anti-concentration that those circuits sometimes have. It's based on joint work with my collaborators, Nick Hunter-Jones and Fernando Brandão. Okay, having trouble advancing the slide here. Oh, there we go. Okay. So the plan for the talk is going to be, first we'll define what is anti-concentration. We'll give a few reasons to care about anti-concentration in its relationship to the question of when quantum circuits can be efficiently simulated classically. We'll state the results of the talk and a few takeaways from those results. And finally, spend a bit of time talking about the proof method, which is based on a mapping from random quantum circuits to classical stat-mech partition functions. So the setup for this talk is a familiar one. We have an n-qubit quantum system that experiences a series of gates, followed by a projective measurement on all n qubits, giving rise to a sample from some probability distribution Pu over 2 to the n possible measurement outcomes. For the sake of convention, we assume that the first layer of gates is a single qubit layer. And then after that, we have 2 qubit gates acting on each of chosen pairs of qubits. We call these random quantum circuits because every time we have a gate, we'll choose that gate uniformly at random from the Haar measure. So in the next, in this slide and the next slide, I'm going to discuss what anti-concentration is. Here, I'll give sort of the mathematical definition, and then on the next slide, I'm going to give more of the way I think about it intuitively. The definition of anti-concentration relies on this quantity called the collision probability, which is just, you get it when you take 2 copies of the circuit and you take 2 samples independently from the measurement outcomes of those two copies. And then the collision probability is the probability that those 2 samples agree with each other. It's given mathematically just by the sum over the 2 to the n output probabilities squared, and then the expectation of this quantity when you choose the circuit randomly from the random quantum circuit ensemble. Because of the symmetry in the random quantum circuits, you can pull out a factor of 2 to the n. Each of the 2 to the n terms has the same value under expectation, and look at the expectation of a single output probability squared. And then in this last line, it's just the same equation, but written to highlight the fact that this is fundamentally a second moment quantity. So we have 2 copies of the unitary, 2 copies of its adjoint, and we're taking the expectation over this whole thing. So we can compute the collision probability in a few specific cases. So in the case that the output distribution is the uniform distribution, which you can get, for example, if you perform a Hadamard gate on each of the n qubits, then the collision probability is 1 over 2 to the n, and this is its minimal possible value. If you do a global Haar transformation on all n qubits, so a 2 to the n by 2 to the n Haar random unitary, then you get a collision probability that's roughly twice as large, 2 over 2 to the n plus 1. And if you do a single qubit gate on each of the n qubits, but no 2 qubit gates afterwards, you just have a non-interacting system, then you get a collision probability that's 2 to the n over 3 to the n. And the point of anti-concentration is to differentiate between these last 2 situations. We define anti-concentration to be when the collision probability is at most a constant factor larger than it is in the Haar, the global Haar case. So this constant factor we choose to be 2, but this is sort of an arbitrary choice. So one thing I'd like to highlight is that if you're familiar with the concept of an approximate 2 design, you'll see that the approximate 2 design property immediately implies the anti-concentration property, because this second moment quantity can just be replaced with its value as in the global Haar case up to some small correction, immediately implying anti-concentration. So 2 design implies anti-concentration, but one theme of this talk is that the reverse is not true. Actually, we'll be able to see that anti-concentration is reached at a much shallower depth than what's needed for the 2 design property. Okay, so That was sort of the mathematical definition, but here's kind of another stab at it in a more intuitive way. So because the collision probability is related to the second moment of this random variable PU, this output probability, it's therefore related to the variance. So a higher collision probability means larger variance in the collision in the output probability. So we can plot a histogram of the output probability in these three cases. In the first case, where the output distribution is uniform, right, all of the output probabilities are 1/2 to the n. There's no variance around the mean. They're all exactly equal to the mean. And we have the situation on the left. When the output is anti-concentrated, but not uniform, there will be some variance around the mean. The mean is still 1/2 to the n, but sometimes the output probability is a little bit larger, sometimes it's a little bit smaller, and you get a distribution that generally looks something like this in the middle. And this contrasts with the not anti-concentrated case, where the collision probability is much larger than 1/2 to the n. And although the mean is still 1/2 to the n in this case, you have a few very heavy outputs in your probability distribution that have a lot of the probability mass concentrated on those outputs. So it's not anti-concentrated. And conversely, in order for the mean to still be 1/2 to the n, you need a lot of the output probabilities, most of the output probabilities, to be very close to 0, much smaller than the mean. And so the kind of point of anti-concentration is to differentiate between this last example and the middle example. And the picture that we should have in our mind is that when we start our circuit, if we don't do very many gates, we're going to be in the right example. And as we do more and more random gates, we slowly approach this sort of middle situation as we reach anti-concentration. Okay, so you wouldn't be blamed if you didn't see why this was important. I don't think it's immediately obvious at all. And the reason that we'll give for why we should care about anti-concentration is related to the question of when are quantum circuits hard to simulate classically. So there's kind of dueling reasons to care about anti-concentration in this context. The first one is that anti-concentration has been an ingredient of certain mathematical arguments that underlie these quantum computational supremacy proposals. So the idea there is you want to try to show that sampling from the output distributions of these quantum circuits is hard, and anti-concentration has been one of several ingredients to prove that fact under certain circumstances. This is sort of converse to another reason to care about anti-concentration, which is that in certain cases, it actually implies that that quantum circuits are easy to simulate. So one example was given in a paper by Bremner, Montanaro, and Shepard, where they looked at IQP circuits that have depolarizing noise applied at the end of them. And they gave an algorithm that runs in polynomial time, assuming anti-concentration for this situation. Similarly, Gao and Duan studied a situation where you have random ensembles of circuits that have local depolarizing noise inserted into them in various places. And they showed that this approaches the uniform distribution, which of course can be trivially simulated classically. But this result also only held assuming anti-concentration, or at least it could only be proved to hold assuming anti-concentration. Okay, so another example of where anti-concentration has arisen recently was in a paper last year by Barak, Chow, and Gao. And they studied the quantum circuits that Google had been using to try to demonstrate quantum supremacy, these 2D random quantum circuits. And in particular, Google had proposed a benchmarking metric called the linear cross-entropy benchmarking metric for these circuits. And the Barak Chow Gao paper attempted to develop an algorithm that could score well on the metric despite not actually simulating the circuits. So they gave this algorithm, and they showed that it could score and it could achieve an epsilon score on this metric in a certain amount of time. But the amount of time that it took depends on this collision probability, the Z quantity. And in particular, you have to, in order for this to be a polynomial time algorithm, you'd have to reach this anti-concentration property within a certain depth. And so in 1D, for their application, they needed anti-concentration within log n depth, which they proved. And in 2D, they needed it to occur within square root log n depth, which they conjectured. And so we'll come back to this, this conjecture later after we state our results. Okay, so that kind of concludes the beginning, where we've defined anti-concentration. We've tried to give some motivation on why we care about anti-concentration. And now I'd like to get a little bit into the results of what we show. And first, I'm going to just mention what I mean when I say a random quantum circuit architecture. So a random quantum circuit architecture in my language is just a method of choosing the circuit layout. So of course, once you've chosen the layout, once you've chosen where the gates are going to go, you always choose those gates to be random according to the Haar measure. But you know, you have a choice as to like how you arrange them in the first place. And we importantly develop a framework to study anti-concentration that applies in any architecture. So, you know, if you give me an architecture, I can kind of apply this framework to that architecture. But in particular, we study two architectures. The 1D architecture, where we arrange the gates in a ring, and then we apply nearest neighbor gates. We arrange the qubits in a ring, and we apply gates on nearest neighbor pairs of those qubits. And then secondly, the complete graph architecture, which can be thought of like this. Imagine you just have a bag of all the qubits, and you draw 2 qubits at random from the bag, and you apply a 2-qubit gate on them, and then you put them back in the bag, and you keep doing this at random. So every 2-qubit gate is on a random pair of qubits, and there's no sense of spatial locality in this system. It would be interesting to analyze specifically these higher dimensional architectures like the 2D or 3D architecture, but we don't provide any rigorous results in those cases beyond what we can say applies in general. Okay, so this slide, I'm just trying to lay out the results of the paper, which I'll go through now. So the main idea is that we have this collision probability quantity, this Z quantity, and we show upper bounds and lower bounds on that quantity as a function of the number of gates in the circuit, so the circuit size S. Because we define anti-concentration to be the point at which the collision probability falls beneath twice its limiting value, this Haar value, ZH, these upper and lower bounds on Z give us upper and lower bounds on when we've achieved the anti-concentration property. Now, this is all stated in terms of the circuit size, S. If you want to talk about the circuit depth, you can also do that. So in 1D, you can just pack all of the gates neatly into layers. And so you get a depth that's just twice the size divided by N. And in the complete graph case, it's not quite as simple because you won't necessarily be able to pack the gates nicely into layers. And so you pay an extra factor of log N when you do this. But we think of the size as kind of the more natural way to talk about the anti-concentration condition here. So yeah, so here are the results. In the 1D case, this Barak-Chow-Gao paper that I mentioned previously had shown an upper bound of n log n with a certain constant prefactor for the anti-concentration size. We confirm that bound in our framework, and we provide a matching lower bound that has even the same constant prefactor of the n log n. Then for the complete graph case, we show a similar thing. We show an upper and lower bound that matches up to the constant prefactor. Previously, the best known upper bound for this architecture was order n log squared n. So we've been able to shave off a factor of log n and also pin down this constant prefactor precisely. And then in general, importantly, we show a lower bound of n log n, order n log n, which means that no matter how you want to arrange the gates of your circuit, you need at least order n log n of those gates in order to possibly have achieved the anti-concentration property. Additionally, on the upper bound side, we show a weak upper bound of order n squared gates, although we conjecture that this can be improved to n log n in general, assuming only a kind of weak condition that the circuit is relatively connected, right? You can't have a completely disconnected random circuit and expect it to anti-concentrate. Okay, so that's the results. What are the takeaways? So for me, there's a couple of takeaways. First of all, I think the fact that the upper and lower bounds match even up to this constant prefactor indicates that this StatMech method that I'll explain later is quite powerful and perhaps motivates trying to find more problems to apply it to, where we might be able to generate sharp bounds like this. Secondly, I think the fact that anti-concentration occurs after only n log n gates in both this very spatially local architecture and a very spatially non-local architecture sort of indicates that this is much faster than we expected, because previously we had been using the two design property to imply anti-concentration. But two designs are much stronger. In 1D, it takes linear depth, so it takes order n squared gates to reach the two design property, but it only takes n log n gates to get to the anti-concentration property. So anti-concentration is actually achieved much faster than the two design property. And so for all these applications we mentioned before, perhaps we can access them at a much shallower depth than previously had been thought. And then additionally, where these results settle a couple of conjectures that had been made in previous work. So these Harrow and Maraban paper from 2018 had looked at this complete graph architecture and conjectured the constant prefactor, but we've pinned it down to be 5/6. And then the Barak Chow Gao paper I mentioned had conjectured square root log n depth lower bound, upper bound, but we contradict this by showing a lower bound of log n that applies in any architecture, so including the 2D architecture. Although I'll mention for the application that they used, they might be able to prove their claim in some other way, just not directly using this anti-concentration route. Okay, that concludes the results section. And in the remainder of the talk, I'd like to discuss the methods, because I think beyond kind of the high level, the results that we've stated previously, I think the methods give sort of an appealing picture of what's going on with anti-concentration and how do we know anti-concentration is happening. So hopefully I can communicate that to you in the remainder of the talk. So recall that the quantity that we're trying to compute is this collision probability. It's an expectation value over the random quantum circuit, 2 copies of U, 2 copies of its adjoint. But because we've chosen the gates independently from one another, all to be random, instead of doing an expectation over the whole circuit, we can just do the expectation over each individual constituent, sort of a trivial observation. But how do we perform these expectations over these gates? To do that, we rely on previously developed formulas for computing these Haar expectation values. So here I've given those formulas, first in standard notation and then as a wiring diagram. However, it's not too important to focus on the details. There's really one takeaway from this slide, and that's the following. So on the left-hand side, we have the expectation value we're trying to compute. It depends on this randomly, this continuously varying unitary U. And on the right side, we just have 2 terms. So the left side is sort of complicated. We don't really know what to do with it. The right-hand side is much less complicated. It's 2 terms. The first term is just a number. This thing in parentheses is just a number. You can evaluate it times the identity operation, which just takes these 2 copies of the system and doesn't do anything to them. Because remember, on the left side, we have 2 copies of the unitary acting on 2 copies of the system. The identity operation just takes those 2 copies and does nothing. And then in the second term, we have another number. And then we have the 2 copies of the system and we swap them. That's this S operation. So those are the only 2 terms, and they're rather simple. And so that's nice. So what do? We take this circuit with all these constituent unitaries. We apply this formula to each one individually. It gives rise to 2 terms for each of the gates, and then we expand it. And we have this big sum over many terms, each of them associated with an assignment of identity or swap to each of the locations in the circuit. And we can organize these locations into what we call a trajectory. And I think this is best explained by an example. Hopefully it will make sense just once I go through this example. One example is the example is as follows here. So if we start with this first layer of single qubit gates and we pick an assignment to each of the gates. So here we've chosen identity, swap, swap, swap. And then we imagine doing the first gate. So the first gate acts on the first and second qubits. And the rules are that when we have 2 qubits that have disagreeing labels coming in, so we have an identity and swap in this case, we have to flip one of them so that they agree. So in this case, we flip the second qubit so it agrees with the first qubit, and they're both identity. Because no gate acted on the 3rd or 4th qubits, we have to leave them to be the same value that they were before. So we leave them both as swap. And then in the next gate, we are acting on the 2nd and 3rd qubit, which again disagree, and so we flip one of them so that they agree. Again, we flip one so it agrees. Now in the 4th step, we're acting on a pair of qubits that already agree. They're both already swap, and so we don't flip either of them, and we leave them the same. And then the final step, we do another flip. So this represents a trajectory, a valid trajectory that has some non-zero contribution to the collision probability. Its contribution is given by this weight formula, which is very simple. It's just 2/5 for each time we made a flip. So here we flipped 4 bits. And so the total weight of this term in the sum is going to be 16 over 625. So basically, you can imagine forming trajectories this way, and each of the trajectory formed this way will have some different weight in the sum. Okay, here's another example. We start with a certain configuration, SI, SI. We make a flip in the first step. We make another flip in the second step. And now we're at the configuration that's the identity, 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 identity configuration. We call this a fixed point because once we're in the all identity or the all swap configuration, no matter what gates we do hereafter, we won't make any flips at all. The weight of this configuration is only 4 over 25 because we've only made 2 flips, much larger than the previous example. And this highlights an important takeaway, which is that the trajectories that quickly reach a fixed point generally have larger weight than those that stay far from a fixed point for a long time, because they generally have fewer flips. Okay, so those were 2 examples, but here's the formula that summarizes the previous slides. So this is the collision probability Z expressed as a sum over all possible trajectories formed in the previous, like the previous examples, where the weight that each trajectory gets in this sum is equal to 2/5 to the number of bits that get flipped during the trajectory. So if you look at this for a second, you see that it's basically exactly equal to a partition function of a StatMech model. So if you think of these identity and swap labels as spin up or spin down for an Ising system, then this is exactly an Ising-like classical StatMech model. And these quantities 2/5 the number of bits flipped, that's like the Boltzmann factor for this for a certain configuration in the StatMech model. In fact, this is very similar to a ferromagnetic Ising model because you can see that the weight of a certain configuration is larger when nearby spins are agreeing with each other. So the spins would rather agree than disagree, although it's not exactly the same model as the Ising model. Okay, so now that we've kind of established this mapping, mapping between the collision probability and this sum, we'd like to be able to evaluate the sum. But we can only evaluate it exactly in one particular limit, and that's the limit that we have an infinite number of circuit elements. So if we have an infinite circuit size, then we can expect every trajectory to eventually reach one of these fixed points, which makes it easy to evaluate the sum. We find that it's equal to this Haar value, 2 over 2 to the n plus 1, which is really what we should have expected in the first place. If this wasn't the case, we should have been worried. And that's because if you imagine a random quantum circuit ensemble made from local constituents, and you just do these local constituents forever, eventually the ensemble should approach the same ensemble as if you did just one big Haar random gate. So this is the value that we were expecting to get, and we got it. That's good. But it also exposes an important observation, which is that when we cut off the circuit size at a finite value, so we don't let them be infinite, then some of these trajectories will not have reached a fixed point yet. They'll still be in the process of flipping bits when we end the circuit. And this means that they'll be overweighted because remember, when we flip bits, the weight goes down. So this kind of explains why the collision probability is larger than its limiting value, is larger than this Haar value when we have a finite size circuit. Okay, so the technical challenge then is to kind of take a finite size and try to evaluate or bound this sum even for a finite size. And I guess to kind of sketch what's going on here in the complete graph case, I've prepared this slide. Remember in the complete graph case, we have this bag of bits and we're drawing random pairs of bits. And then if we draw a pair of bits, like if we draw one that's assigned identity and one that's assigned swap, we're forced to flip one of them so that they agree, and we throw them back in the bag. And we draw a new pair, we flip one potentially, and we throw them back in the bag. So what's going to happen here? Typically the bag will start with like some fraction or identity, some fraction or swap. We'll start drawing them, but quickly what happens is we kind of approach either the case that most of the bits in the bag are assigned identity, or most of them are assigned swap. And that's what this plot is trying to show, that we kind of have this bifurcation that happens very quickly, where the trajectories either approach the all identity or the all swap configuration. You can also see here where the log n dependence comes from. And that's just because as the like composition of the bag approaches the all identity or the all swap, it also slows down as to how fast it's approaching the fixed point. So this, if you go through the details, you clearly see the log behavior as you get close to the fixed point. So the technical challenge is to like consider a finite value for the circuit size, say size equals 200, and try to figure out the probability that these trajectories have already reached the fixed point by that size. And if not, how far away from the fixed point are they? Okay, so that's how it goes for a complete graph. The last thing I want to say is about the 1D case, which is mostly the same. The only difference is that we can really think of the configurations in terms of their domains. So because we have spatial locality, we can group contiguous sets of spins that all are identity or all are swapped together, and think of the borders between those domains as being domain walls. When we apply gates on the system, these domain walls will move around, and we can look at a trajectory in the as in the following picture, where this is a picture of how the domain walls evolve. Then our sum is just a sum over all these possible domain wall evolutions, which we can analyze by kind of grouping them into parts where all the domain walls annihilate and other parts where none of the domain walls annihilate. And here again, you can see the log dependence, because as you make the depth of the circuit longer, the weight of these second kinds of contributions, where we have domain walls that exist throughout the entire system, are decaying exponentially in that depth. If you want the full details,
sorry,
look at the paper.
Ask you to conclude. Oh, are you?
Yeah, sorry. Okay, yeah, here we go. The last slide, just the conclusions and the open problems that we have. But yeah, I'll just leave this slide up, and if there are any questions now, I can take them, or later.
Yeah.
On the
yeah, so Nick already took care of some of them for you, but so I'll ask, there was one question by Guillaume. So he asked, if you replace the constant Chu in the definition of anti-concentration, does this affect the prefactors?
No, so happens? Yeah, so that's one of the reasons why it doesn't really matter. So basically, if you look at these, if you look at the main results here, if you change the constant factor of 2, then this will change the constant prefactor of the linear term that's hidden in this big O notation. It won't change the constant prefactor of the n log n. So this kind of gives a reason to believe that this definition of anti-concentration, where we've chosen a specific value of 2, is sort of a fine one that's robust to different choices.
I see, thanks. And maybe you have time for one quick question. I think the other one was already answered in the chat. So the question by Dhruv is, can Clifford circuits anti-concentrate in what depth?
Yeah, so actually, because our methods only rely on the second moment, you know, like because the collision probability is only related to the second moment, the value of the collision probability is exactly the same if you choose the gates uniformly from the Clifford group as if you choose them uniformly according to the Haar measure. So actually, all of these results are exactly the same for Clifford circuits. The collision probability is exactly the same. So yeah, Clifford circuits will have the exact same anti-concentration properties.
I see. Well, and then there was one question by Andras. Your log n lower bound of the depth means that the Barak and all result cannot spoof the cross entropy?
Yeah, so that's right. I guess I think it's still a quasi polynomial time algorithm, even in 2D. So I mean, of course, like Google had these deep circuits. The Barak et al. Algorithm only was ever going to try to work for log n or square root log n depth circuits, but they did need this anti-concentration property to hold in order for the spoofing to work, even for the square root log n depth circuit. So without anti-concentration, they're not able to quite prove that it works, even in this shallow version. But it's still possible that the algorithm works, just that it needs a proof that doesn't rely on the collision probability.
Okay, thanks a lot. So there were some other interesting questions in the Slack channel, but I think we can discuss them then in the roundtable after the talk. Unfortunately, that's all we have time for. So thanks again for Alex for the very nice talk.